All right, so looking at this class starter today, I think a lot of this is going to assist you with those questions at the end of your project. Okay, so I really want to, I know on those questions, you're going to have to identify the period, the amplitude from equations. You're going to have to write the equation from a verbal description like in number 2, or from a graph like in number 3. Then you're even going to have some real application kind of problems similar to what we have in number 4 on this class starter. So looking at number 1, it says to determine the amplitude and the period of each of these functions. We'll have to hold off on C until after we go through the graph of tangent. But for A, what would be the amplitude? 4. And then for the period, how do you determine the period of a sine or cosine function?
2 pi over b.
2 pi over b. So you're going to do 2 pi over 3/4, and then simplify that, and you get 8 pi over 3. Good. Okay. Because when you do 2 pi over 3/4, instead of dividing by 3/4, we're going to multiply by 4/3, and that would give us 8 pi over 3. Okay. For part B, what's the amplitude? 3, good. What does that negative in the front tell us? Just reflected over the x-axis, but the amplitude is a distance. It's half the difference between the maximum and the minimum value, which is going to be a distance. And so therefore it has to be positive, and so we call it 3. And then for the period, we're going to do 2 pi over 4, and what is all that reduced to? 8. Period would just be 8. So if we were going to graph this one, we would actually label the x-axis not in terms of pi, but in terms of regular old numbers, because now one cycle of cosine is going to take 8 units. So we just go from 0 to 8 would be one cycle. So it would make more sense in that case to label everything in terms of our integers on the x-axis. Whereas in part A, the period is still in terms of pi, so it would make more sense to label the x-axis in terms of pi. We're going to practice a little bit towards the end of class about graphing, so we'll talk a little bit more about it when we get there. Okay? And like I said, we'll come back to 1C, and we'll come back to number 2 after we've talked about phase shifts and vertical shifts. So let's look at number 3. This time, we're given the graph, and so we're going to have to make the decision if this represents a sine function or a cosine function. And then from there, discuss the amplitude of the period. So for A, would you call that a sine function or a cosine function? Cosine. It's all about how the graph crosses the y-axis. If the graph crosses the y-axis at either a maximum or a minimum, it's cosine. If it crosses the y-axis in the middle of a cycle, then we'll call it sine. And in this case, we can see that it crosses the y-axis down here at a minimum. In fact, normally, like the parent function for cosine crosses at a maximum. So what do you think is happening here if the graph's crossing at a minimum? It's been reflected over, which means that it's going to have a negative out front. Okay. Right now, let's talk about the amplitude. What's the maximum value for this graph? 3. Okay. It occurs right here, which we'll assume that to be 3. The minimum occurs at -3. So, this one is kind of situated around the x-axis. The x-axis kind of goes through the middle of it. And so it goes up to 3 and down to -3. The amplitude's easy to determine in that case. What is it? 3. And then for B, that is either determine what one period length is, or one cycle length, and then set that equal to 2 pi over b and find b, or count the number of cycles between 0 and 2 pi. So let's try that. It starts here at 0. There's one cycle, right? Here's another cycle. And there's a third cycle. And that's when we got the 2 pi. So what would b be? 3. So that graph is -3 cosine of 3x. And we can verify that because we could go to our calculator and we could graph -3 cosine 3x and see if it looks like that. All right, for b, do you think that that is a sine function or a cosine function? Yeah, it's a sine function because when it crosses the y-axis, it's right here, and you can see that's in the middle of the, the halfway between its maximum and minimum values. So it's kind of in the middle of that cycle. Let's determine amplitude. What's the biggest value? And the smallest. So the difference between those is, the difference is 4, and half that difference is 2, so the amplitude is 2. But there has to be a vertical shift in this graph. So because if the amplitude were 2, then we would expect it to go from -2 to 2. But what's happened here? It's shifted up 2 units, and so the vertical shift means at the very end, we're going to put a +2. Just like for all of our other functions, a vertical shift is adding or subtracting a number at the end. The horizontal shift is adding or subtracting x inside the function. But here, when we put that +2 at the very end, and it's not in parentheses with x, then that means that the entire graph has been shifted 2 units up. And then to determine b, we'll count the number of cycles between 0 and 2 pi. So I'm going to start here where it crosses the y-axis. There's one cycle. There's another cycle. So how many cycles do we have? So this is 2 sine of 2x plus 2. Everybody good on 3a and 3b? All right, finally, number 4 really is really quite easy if you think about it. It says the current I in amperes flowing through an alternating current circuit at time t in seconds is given by this function I of t. First off, I ask, what's the period? Well, period is 2 pi over b. And what's b in this case? 30 pi. So what does that reduce to? 1/15. And so that would mean that the period is 1/15 seconds. Okay, because the period is the length along the x-axis, or in this case the t-axis, because the variable is t where x normally is, and t is measured in seconds. So every 1/15 of a second, then this current is repeating itself. Then it asks for the maximum current, like the biggest Y value, the biggest value for I. Anybody want to take a shot at that?
90.
Not 90, but you're on the right track. 120. Why'd you say 120? That's the amplitude, right? And the graph would go up to 120 and down to -120. Except, what does that tell you to do? Shift everything up 30 units. So the amplitude being 120, that would normally be your maximum value, except in this case, what have we done? Shifted 30 units up. So what does that mean the maximum value would be? 150. Okay? And the minimum would be 90. So if you want to calculate a maximum, not only do you have to take the amplitude into consideration, but you also have to take into consideration vertical shift. Okay? On those problems at the end of your project, I think you have 2 that kind of talk about that. You have one where I think it's talking about the wave height of waves hitting up against a pier or something, if I remember correctly. And then you have another one that talks about the bear population in a certain area. And population, particularly animals, follows cycles, and sine and cosine are really good models for that because oftentimes those animals, or the population of those animals, is dependent upon other factors like the temperature, climate conditions, availability of food. So take bears for an example. If there's not a lot of food available to them, then a lot of them will die off. But as that population dies off, then the amount of food that is available will sustain that population, allow that population to grow again. But animals can't help themselves. They eat quickly and they reproduce quickly. So once that population comes back up, then now we're at this stage again where we don't have enough food to sustain the population. So the population is going to come down again, and then eventually will grow again. So it follows that cycle. And so sine and cosine functions are really good models for that. And so you can use the idea of the amplitude plus or minus the vertical shift to determine the maximum and minimum values of the population. Everybody good so far? All right, let's get our flip book, and let's do tangent together. And then we're going to finish off on looking at phase shifts and vertical shifts of all of our trig functions. But tangent looks a little different than sine and cosine. A lot different.
We're going to have fun.
We started with sine and cosine. Those look very similar. There's a lot of similarities between them. Obviously, some differences, but it makes sense to do those together. Then it makes sense to follow up with cosecant and secant, because if you'll recall, those graphs are heavily reliant on sine and cosine. Secant is the reciprocal of cosine, and so really what we did was we graphed cosine first, and then use the places where cosine was 0 to identify vertical asymptotes for secant. And then any values on the graph of cosine, we just found the reciprocal, and that gave you a value on the graph of secant. And so it literally was that cosine became flipped over, and that became the graphs of secant, which, maybe making the idea that secant's the reciprocal, which kind of flips over the graph, flips over the value, and that kind of makes sense. But tangent, kind of save this one a little bit because it's going to use some of those characteristics that we've talked about. But really, by definition, or by one of our identities, what is tangent equal to? Sine over cosine. Okay. So because tangent really relies on both values for sine and cosine, then there's going to be a lot of similarities or connections between the graph of tangent and sine, tangent and cosine, even if it doesn't look like it initially. And then there's obviously going to be some differences now because tangent's relying on both values, whereas like cosecant was only relying on the values of sine. Secant was only relying on the values of cosine. But just like with secant, secant's equal to 1 over cosine. So what happened on the graph of secant every time cosine was 0? What did the graph have? Yeah, vertical asymptote, right? Every time cosine was 0, then secant, which is 1 over cosine, is undefined. And because it's undefined, then, we talked about it could either be a hole or a vertical asymptote, but we eliminated the possibility of it being a hole in the graph, and it became a vertical asymptote. Well, that's still true right here, because you'll notice that cosine is in the denominator. So anytime that cosine is equal to 0, what can you tell me about tangent? Cosine 0, what can you say about tangent? It's going to be undefined, and it's going to have a vertical asymptote. So tell me all the places where cosine is 0. You should have the graph right in front of you. All right, negative pi over 2, pi over 2, 3 pi over 2, negative 3 pi over 2, all the pi over 2s, right? So when we go to graph this, and we'll graph it from negative 2 pi to positive 2 pi. That makes it easy to label these the x-axis. All the places where cosine is 0, which are all pi over 2's, then tangent is going to be undefined. And so we'll have vertical asymptotes in all those places. All right, well, what about all the places where sine is 0? Then tangent's going to be 0, right? Because what happens when you get a 0 in the numerator? It equals 0, right? So tell me all the places where sine is 0. Negative pi, negative 2 pi, pi, 2 pi, and at 0, right? So at all the multiples of pi, sine equals 0, which means the tangent's going to equal 0. So we can put points on all the multiples of pi. If you've started to write some of your descriptions, maybe for sine and cosine, I suggested to you that you identify some places where the graphs of sine and cosine intersect. Has anybody found some of those places where those graphs are going to intersect? Yeah, where? Say again?
And then the secant. That's what it would be.
Okay.
At the very end.
But what about for sine and cosine? What were points of intersection for sine and cosine? And even if you haven't graphed them, you ought to be able to reason that out. A point of intersection means they have the same point. They have the same value. Pi over 4. Where else? Right, negative 3 pi over 4, which would coterminal angle of that be 5 pi over 4, right? So at pi over 4 in the first quadrant and in the third quadrant are going to be the places where there's going to be a point of intersection. They're going to have the same value. Well, if tangent is sine over cosine, and you're telling me that at those places sine and cosine have the same value, then what is tangent going to be equal to at those places? 1, right? We know that. I mean, at pi over 4, the tangent value is 1. Okay, what about at like 3 pi over 4? What's the tangent value? That's in the second quadrant. What is it going to be? Negative 1, because in the second quadrant, sine's positive and cosine's negative. And at 7 pi over 4, which is in the fourth quadrant, it's going to be negative 1 because cosine's positive but sine's negative. So when you think about like pi over 4, which would be halfway between 0 and pi over 2, we're going to be at 1. At 5 pi over 4, we're going to be at 1, because that's in the third quadrant. At 3 pi over 4 in the second quadrant, we're going to be at negative 1. At 7 pi over 4, we're going to be at negative 1. That's in the fourth quadrant. At negative pi over 4, that's in the fourth quadrant, would be negative 1. Here, between negative pi over 2 and negative pi would be in the third quadrant, would be a positive 1. And you just kind of see it alternating here at all the pi over 4s, switching between negative 1 and 1. And for me, that's really enough to draw the graph. We know how a graph behaves as it approaches a vertical asymptote. We know that it gets really close to it and continues to get closer and closer to it. And so for each of these, and between all these vertical asymptotes, it's going to go along the vertical asymptote, through those points, and then along the next vertical asymptote. So here would be the graphs of, or the graph of tangent. All right, so let's see if we can describe tangent what would be its domain?
X such that x is not equal to pi over 2 plus or minus pi n.
Good, right? So in all the places where cosine was 0, then tangent's undefined there. So the domain is all of the x's such that x does not equal all the places where cosine is 0, which is pi over 2 plus or minus pi n. What's the range for tangent? All real numbers. And remember how the range for sine and cosine is between -1 and 1, which then became the domain for inverse sine and inverse cosine. Well, now the range for tangent is all real numbers, and the domain for inverse tangent was all real numbers. We could take the inverse tangent of 3. We could take the inverse tangent of -4. We can get values for that. We couldn't do it for inverse sine or inverse cosine, but we can for tangent. Is there any symmetry?
Origin.
Yes, origin symmetry. Good. Which means it is odd. Is it 1 to 1? No, because just like sine and cosine, it's periodic, so it repeats itself over and over again. And that's why when we talk about inverse sine or inverse cosine or inverse tangent, we have to restrict ourselves to be between, like in this case, it would be between -pi/2 and pi/2. But it's not 1 to 1. Does it have any asymptotes? Yeah. Yeah, and all the x is such that x is equal to pi/2 plus or minus pi n. So the restrictions on the domain are the asymptotes, and that's why there are restrictions on the domain. Intercepts.
So that's associate x equals pi plus or minus pi.
Okay. All the x's such that x equals 0 plus or minus pi n is really all the intercepts for sine are also the intercepts for tangent. Hopefully that makes it into the paragraph that you write when you compare tangent and sine. Okay, their intercepts are the same. Y-intercept? 0. Does it have a minimum? Maximum? In behavior? And in behavior? Because, you know, I guess you might think it's going up towards positive infinity, but, you know, at some point it comes back down here and starts over again. So it's never at a point where it's just always going towards positive infinity. And it always has to start over again and then start going that direction. Let's talk about the period and the amplitude for this. First off, amplitude, by definition, is half the difference between the maximum and minimum values of this function. What's the maximum? Infinity, and the minimum? Right, and those aren't numbers, so I can't say the difference between those two. I mean, the difference between those two is what? 2 infinity? And half the difference of that is infinity again? No, there is no amplitude. And so tangent and cotangent have no amplitude at all. But they do have a period. And the period is how often the graph repeats itself. And how, you know, if you look at it, each of these little branches is one repetition. So how often does it take for them to repeat? So like this first one goes from -pi/2 to pi/2. How long is that? Pi. Okay. Next one goes from pi/2 to 3 pi/2. That length is pi. So its period is pi. Whereas for sine and cosecant and secant, period is 2 pi. For tangent and for cotangent, the period is only pi. And actually, to find the period, we're going to say pi over b as opposed to 2 pi over b. Okay? All right, why don't I give you a few minutes and you try and graph cotangent? Yeah, over the parent function b as well. right, try graphing cotangent. All right, let's talk about cotangent. Just in general, tell me what the graph looks like. Yeah, it looks like we reflected it over the x-axis, right? Taking tangent, reflected it over the x-axis, and it's been shifted some, hasn't it? Like now, where are the vertical asymptotes? At all the pi's, right? Really, at all places where tangent crossed the x-axis, now cotangent has vertical asymptotes, and at all the places where tangent had vertical asymptotes, cotangent crosses the x-axis. So it's been shifted over a little bit, it's been reflected over the x-axis, and that's what cotangent looks like. All right, let's fill in the descriptors. What is the domain? All the x's such that x does not equal 0 plus or minus pi n. So really, the x-intercepts for tangent now become the places where cotangent's undefined. The range, all real numbers, symmetry. I think it has origin symmetry.
You can have origin symmetry even though it doesn't go to the origin.
So just imagine taking any piece of it and reflecting it over both the x and the y axis, and does it match up to some other piece? And I think if you kind of practice that way, then you'd say, yeah, it does have origin symmetry, which makes it odd. It's not one-to-one. Does it have asymptotes? Obviously, yes. Have all the x's such that x equals 0 plus or minus pi n. So all the restrictions of the domain are the places where there's vertical asymptotes. That's why they're restrictions of the domain in the first place. Any x-intercepts? Yep, all the x's such that x equals pi over 2 plus or minus pi n. So all the vertical asymptotes of tangent, their x-intercepts of cotangent. It should be really, really easy for you to start writing the descriptors that relate tangent and cotangent, right? And there's so many similarities between these, or connections at least between those. There's no y-intercept, there's no maximum, there's no minimum, there's no end behavior, there's no amplitude, and what's the period? Right. Pi units would be the period for the parent function, and for any other function, it would be pi over b. So with that said, let's go back to our class starter. We should be able to do 1c now. This is a tangent function. What's the amplitude for 1c? There's not one. All right, it's a tangent function. Tangent doesn't have an amplitude.
So let me write it down.
None. No amplitude.
What's the 2? Like, what is it?
The 2 would take the graph and stretch it vertically because we multiply the y coordinates by 2. So like where tangent, where the parent function has like a pi over 4, it's at 1. Now it would be at 2. It stretches it out vertically, but it still doesn't have an amplitude. And then what would the period be for 1c? Pi over 4. Good. So now instead of, everything, all the branches of tangent having a length of pi units, now it's going to be a length of pi over 4 units. So it's really going to be compacted now. Okay. All right. Everybody good with 1c? All right, so the last thing that we got to talk about in relation to the graphs of trig functions would be their shifts, their phase shifts and their vertical shifts. And we've really already talked about vertical shifts. It's not any different than all of our other parent functions that we discussed. If we add or subtract the number at the end, that's going to shift our graph up and down. So it's not really anything new. But we do have something that's called a phase shift. And really, a phase shift is nothing more than a horizontal shift. It's just that for trig functions, we refer to horizontal shifts. as a phase shift. And so a phase shift is going to occur, to answer this question, what is a sine curve, or really any trig curve, has a phase shift when in parentheses we're adding or subtracting a number to x. Okay? Because if there's parentheses, like sine of parentheses x plus pi over 2, then now that's inside the function sine. Okay, so a phase shift occurs whenever you're adding or subtracting a number from x inside parentheses, inside the function. And then a vertical shift occurs when you're just adding or subtracting a number at the very end to the entire function. There's no parentheses involved. So if we put it all together, then here's really what the graphs of sine, or the equations of sine and cosine can look like.
A phase shift occurs when you add or subtract a number within.
Add or subtract number to x inside parentheses, or inside the function. And then the vertical shift occurs whenever it's added or subtracted outside the function, period. Now, the tangent's going to be the same, except there's no amplitude. The period is pi over b, as opposed to 2 pi over b. But the phase shift and the vertical shift will still be the same. Now you'll notice here that when you write out the graph of sine or cosine, same thing for tangent or any of the reciprocal functions, the b is in front of the parentheses. Okay, so it's not attached to the x, it's actually in front of parentheses, and then it's x minus that phase shift. Okay? And it's the opposite sign, same thing for horizontal shifts. If I want to shift to the right, then it's going to be x minus the phase shift. If I want to shift to the left, it's going to be x plus the phase shift. Okay, so it's always the opposite sign of that horizontal shift, and then the same sign for that vertical shift. So let's go back to our class starter, and let's look at number 2. Because in number 2, what it's going to do is it's going to give us a complete verbal description of the function. And what we've got to do is we've got to fill in everything. We've got to fill in A from the amplitude, we've got to fill in B from the period that it's given us, and then H and K from the shifts that are given. So in A, we're told that we want to write the equation of a sine function that has an amplitude of 5, a period of 2 pi over 3, a phase shift of pi over 2 units to the right, and a vertical shift of 3 units down. So it's going to be y equals, it's going to be a sine function.
Is it still the opposite like it was with
Yeah,
the
for the horizontal shift. Yeah. So then we just got to fill in everything based on what's given. Well, we're told that it's an amplitude of 5, so where does that go? Right. We're told that there's a period of 2 pi over 3. What does that mean? It means b is 3, right? And remember the way that it was written, that b value is in front of the parentheses. So it's going to be the sign of 3 parentheses, and then x with the phase shift attached. In this case, the phase shift is pi over 2 to the right, so that means it's going to be x minus pi over 2, because again, we're going to use the opposite sign of what's inside. So if I want to go in the positive direction, this is going to be x minus pi over 2. And then finally, a vertical shift of 3 down means minus 3 at the end. So our equation would be y equals 5 sine of 3 times the quantity x minus pi over 2, and minus 3. And that tells us all that information in the equation.
What if you put the period of for 3 sides of parentheses, like 3x minus 2? Like put it.
Yeah, it would, and it's kind of, when you have it on the inside, it actually ends up affecting the phase shift as well. So you got to have it on the outside to identify the correct phase shift. We had a 3 on the inside, and when we factored it out, now the phase shift would become like 5 or 6. All right, for B, the cosine, we're going to do a cosine function. An amplitude of 2, that's easy, that's just a 2 in the front, reflected over the x-axis. What does that mean? Make it -2. A period of 1/2. All right, well, for cosine functions, the period is 2 pi over b, but I want this period to be 1/2. So I'm going to solve that for b. When I cross multiply, b equals 4 pi. Okay, so that means that b here is 4 pi. All right, a phase shift of 3 to the left, so that's going to be x plus 3, and then a vertical shift of 2 up. So we'll say plus 2. So -2 cosine 4 pi times quantity x plus 3 plus 2. And then finally, a tangent function. That has a period of pi over 2 and a vertical shift of 4 up. There's no amplitude, so we're just going to assume it's 1. Okay. If the period is pi over 2, what's b? 2, because the period for tangent functions is pi over b, so b has to be 2. Is there a phase shift? So we're just going to call it 2x, and then a vertical shift of 4 up. So it's going to be y equals a tangent of 2x plus 4. That's all of these, right? Got anything on this class starter? I think I have a couple other examples. And these are actually practicing how to graph with a phase shift. You're not going to have to do a whole lot of that on your project. You do have to graph some. And one of them has a phase shift, so we'll practice it. So for number 1, we have y equals negative cosine of 1/2 times pi or x plus pi. Okay, that theta is the same thing as x. I'm sure it is x. So let's just practice graphing it. The instructions say just graph 2 cycles. But before we start graphing it, let's start identifying some information that's going to help us for this particular function. What's the amplitude? 1. All right. What is the period? 4 pi. Because we're going to do 2 pi over b. In this case, b is 1/2. So 2 pi divided by 1/2 would become 4 pi. What's the phase shift? All right, pi units to the left. And then is there a vertical shift? Okay. So we know that if we were going to graph this, kind of based on the parent function, we would have an amplitude of 1, so that means to go up to 1 and down to -1. The parent function usually goes from 0 to 2 pi for one cycle, but this one goes from 0 to 4 pi. It's a cosine function, so where does it cross the y-axis?
A max or a minimum since it's
Good, it would be at a maximum, except it's been reflected over the x-axis, so it's going to be at a minimum. So, kind of piecing all of this together, let's just say that, ignore the phase shift to start with. It would cross the y-axis at its minimum, which is -1. And then where would the first cycle end? At 4 pi. For the parent function, where does the first cycle normally end?
2 pi.
At 2 pi, but this one has been expanded out to go all the way to 4 pi. And if you think about the graph of cosine, the parent function looks like this, right? That's one cycle. So halfway between 0 and 4 pi would be 2 pi. Where do you think it's going to be? It would be a positive one, right? Because of the reflection over the x-axis. And then halfway between 0 and 2 pi is pi. Where's that graph going to be? At 0, and then the same thing here at 3 pi. So here would be, and you don't have to draw this in, I'm just going to put it in there for you to see. There would be one cycle for the graph of cosine without the shift, right? And if I were to continue this on, here at 5 pi, it's going to be on the x-axis. At 6 pi, it's going to be up here at 1. At 7 pi, it's going to be on the x-axis. And at 8 pi, it's going to be down at -1. So here would be that next cycle. But what am I doing to this graph? I'm shifting it how? To the left pi. So every single point is going to get shifted pi units to the left. So now this point that was right here is now shifted over pi units to the left. And all of them are getting shifted over. And so here's what this graph of cosine would look like. So what I like to do is I like to graph it without the shift, without the phase shift or vertical shift, just by looking at the amplitude and the period, and kind of get a couple cycles down, and then use that shift to move all the points based on that phase shift, or if there were a vertical shift in the same way, and then kind of drawing the graph from there. Okay? I don't think any of the ones that you have on that project are going to be overly difficult. You only have one that has a phase shift. The rest of them have a vertical shift. But if you just kind of follow that procedure, just graph it without the phase shift and vertical shift first. So simply just, use your amplitude and your period, get a couple cycles on there, and then you're just going to shift it horizontally based on the phase shift and vertically based on the vertical shift. All right, any questions on graphs of trig functions? All right, so your project is due on Monday. If you kind of suggest, you'll have homework tonight, so I kind of suggest that you start working on it. And then if you have any questions tomorrow, I'll be happy to answer them for you. But this is a test grade, so this is not to be a collaborative effort. If you have questions, ask me. And then, questions come up after tomorrow, then you can send me a message and a reminder, or you can email them to me, and I'll answer them as soon as I can. And then tomorrow, what we're going to do is we're going to start moving into our last unit, which is on logarithms and exponentials.